Uh, Welcome. Thank you for listening to my talk. The title of my talk today is a transformer-based semantic engine for healthcare inference and search. This is ongoing work that I'm working on with my student, Mitchell Burke. My name is Ricardo Calix. I'm a professor at Purdue University Northwest. So the topic today, I'm going to describe this project. So as the title implies, is a transformer-based semantic engine for healthcare inference and search. So I'll talk. This is actually a project divided into some individual components and papers. But if you look at the papers individually, it won't make as much sense as if you look at the project as a whole. So I'll talk about the parts that, basically the pipeline of the project, kind of the work that we have done already, and the parts that we are focusing on at this time. So the basic idea, so if I'm going to, I'm using the Zoom element, so I'll be sharing through screens. So I'll be referring to some of the materials. So in essence, I'll be referring a couple of papers. So I'll be referring this paper on a qualitative and quantitative analysis of a transformer-based model for English to Spanish translation using the Ural-Parl data set. So this, Mitchell, my student, and I worked on this. And this is the work where we have done initial work on the transformer itself. So, before we use the transformer for health inference, you can think of as we tune the transformer to see how it works in a data set that is more, more specific for transformers, which would be something like English to Spanish translation. So here we use Ural-Parl's data set, which has over 2 million pairs of English and Spanish sentences. And so this, I'll talk in a moment about the results that we've got for the component of the transformer itself. The other component that I'll talk about relates to this other paper, which is also, Mitch and I worked on this, and it's a corpus of word co-occurrence graphs from medical literature text for semantic inference mapping and question answering. So this also relates to the data set that we want to use to train the transformer itself. So as you can see, there's, the data set that we need, and then there's the transformer itself. And then there's a few things in between of our approach. Additionally, I will point out some of the resources that we have available for other researchers to pursue their work. So with relation to the transformer, you can see the details here, the transformer for English to Spanish translation. The code is on GitHub already, so you can just get it from the GitHub here. The transformer works really well. As can be seen, the statistics of the transformer are here, and it basically, it obtains an average BLEU score for sentences of a length around less than or equal to 25, which is around 39.79, which is a really good BLEU score, and therefore, allows us to think that the transformer model itself is ready, and all we need to provide is the data for it, which the data, by the way, is can be a bit challenging. So that takes us to the data itself, and you can see here we've also made this available in the GitHub. We have here some of the data. So this is just, we did some preliminary analysis in the data set, but if you click on this link, here we have the data set, and I'll talk a little bit about this, of course, today. But that's some of the data set, some of the data that we have, and then some of the challenges. Additionally, as was mentioned in the title, we are actually creating images of the inputs that we want to see. And so you can see that here. I can just click on one of the images. So this is this is a graph, a cluster, basically a semantic cluster, hopefully, of information from health-related literature. So we'll talk about that as well. But so this is some of the materials that go into this. So the first thing I want to talk about, now that I've pointed out the resources and the materials for the work, is I'm going to refer back to the basic idea of it. Okay, so how do you build a transformer-based semantic engine for healthcare inference and search? So the example of, so I'll go over here. So a transformer is basically, so a transformer is a tool, right, that is a deep learning algorithm, basically. It's one of the most recent deep learning algorithms as of 2017. As you saw in my own results in the paper, this transformer for us, as we tested it with an English to Spanish data set, does incredibly well. So it does really well. If you speak both languages and you see the translations, they're really good. And in some cases, it has a tendency to write, sentences that, compared to the original Spanish sentence, this sentence is more succinct, more to the point, and they're good. Obviously, there's a few mistakes also, but it's definitely an excellent tool. Now, a lot of people will talk about transformers out there like GPT, BERT, GPT-2, GPT-3. We decided not to go with one of those alternatives of the pre-trained transformers. We just wanted to build everything from scratch. Okay, and so that's what we are doing here. So now let's talk a little bit about the pipeline of our work. So the pipeline is basically that we want a transformer at the end of it. Okay, we want a transformer at the end of it. So a transformer, basically, the way it works is that, you train it first by giving it pairs of information. So you give it pairs of information. Of info, right? And this can be, for instance, I give it an English sentence and then I give it a Spanish sentence, right? And those are, we got ours, for instance, from the European Parliament. So the idea is that when they have sessions in the European Parliament, they say the same things, but it's things of interest to English speakers as well as Spanish speakers, and therefore you have the translations by professional translators. So a transformer works like this. You train it with these pairs of information, aligned data. The Europarl, has over 2 million of these pairs. And then once the model is trained, you give it another English sentence, and then hopefully it'll give you a good translation of a Spanish sentence. However, this mechanism doesn't just apply to translation. It actually can apply to any other kind of data. So another example of this is questions and answers. Okay, so in the same language. So it doesn't have to be in a different language. So for instance, questions. So what is the cat doing? And then the answer is going to be the cat is sleeping. So that type of sentence structure where it's something like, what is the noun verb, might be then learned by the transformer where it says, well, the noun is, and something related to that verb. So that's basically what transformers learn. They use a mechanism based on attention, which is a really interesting mechanism. And so this is really the key of a transformer, and it learns. They're highly efficient. They run in parallel really well. So they're really fast, and they run in parallel really well. All right, now, however, what are we trying to do? So what we're trying to do, as the title indicates, we are trying to build. So now I've kind of indicated, right, that we want to use a transformer. But what we really want to build is a semantic engine, not necessarily a question answering engine, not necessarily a question answering or anything like that, just something that does inference, right? So a semantic engine for inference and search. So the thing that we want is we want to give it a semantic concept, okay? So we want to give our model a semantic concept of some kind, semantic concept, but from a domain. For instance, from a healthcare domain. Now, this is what we're doing right now, but just, we're trying to build a methodology that is very flexible for all applications, for many areas. But specifically right now, our work is we're looking at healthcare data. So there's a semantic concept, and we want to map to a semantic concept. That's really what we want. Now, we have taken just basically data, text data, from 2 domains. Okay, the 2 domains that we've taken healthcare data from are research papers, abstracts and research papers from, we collected from COVID, given that it's 2021 right now, and COVID-19 is a big issue. There's a lot of papers on that, actually. And so we collected roughly around 50,000 abstracts of these. And then we also collected another area, but an area that we thought was also a little bit related, which is pulmonary. So pulmonary, and we also have 50,000 samples. All right, and this is something that you can see. So if we go to the paper, we can take a look at that. Right, so we've got our. Oh, sorry, this is the wrong one. If we go to the paper, basically this paper is our discussion of the data set that we've gotten. Okay, so we've collected the data on COVID and pulmonary papers, roughly around 58,000 documents, and from there we're going to extract information. Okay, so that's where we have all these documents, obviously, but we want to collect something. So in a perfect world, we would have the COVID sentence, or a sentence from the COVID data set and a sentence from pulmonary data set, and a human would have looked at them and said, okay, these are related. Now, there's some semantic structure and meaning in them. Then we would look at another sentence from the COVID literature, match it to a pulmonary sentence, and a human would do that. But just think about that. I did that twice, and it took me like a minute. So imagine if I want to do 2 million. So transformers, deep learning algorithms in general, require lots of data to learn. And so we can't really do this manually. And so therefore, our goal really of our work has been to create some kind of a, this is what we've collected manually that is similar and dissimilar. You can see we've only collected about 2,000 manually. So it takes a lot of work. And so what we want is to do this in an unsupervised fashion somehow. So that's why we decided that we're not going to use sentences from the documents, because that's too much work. And instead, we went for the solution of just semantic concepts. Okay, so that's why we're calling these semantic concepts. So the idea then is that we go into, so let's move to the next one. We go into the data set, right? So we have now a data set of COVID papers or abstracts and a data set of pulmonary abstracts. Okay, and now how do we extract meaning from them? So a standard approach usually out there is just to apply word2vec. So we have applied word2vec individually to each one of these data sets. So we apply word2vec here, right? And everybody knows about word2vec in machine learning and NLP. And so basically this allows us to take all the words in all these documents of COVID and pulmonary, and now we're going to create the vectors. All right, so we create vectors of the information in here. So the word vectors, basically. Once we do that, we create the vector space, and then let's just call it vector space for COVID and vector space for pulmonary. Okay, so we create both of these vector spaces, and now we have a tool, a new tool that came out recently in 2020. Okay. So we use this tool. There's a research paper on it. You can see it here in the description of the methodology. We are using a tool called Vectograph. All right, so that we used we take the vector graph data and, sorry, the word to vec data, and we use vector graph, which is based on Katrisheva et al. 2019. Okay, so this tool allows us to create basically little clusters, right? So when you saw these figures in the methodology here, you know, we create basically from the word to vec data for COVID and for the word to vec data from pulmonary, we create these clusters. These clusters have on average about 11 words. And what's important about them is they basically vector graph grabs a word, what is called a central word, and based on its algorithm, it actually finds the closest 10 words, let's say, and then it finds distance metrics. Okay, so it finds distance metrics between the words. Okay, so what we do then is now we have for every word to vec space that we created. Go back to the slides here. For every word to vec space that we created here, now we apply vector graph. Okay, so vector graph and vec to graph. Okay, so we apply vector graph to both of these spaces, and this will produce now for us a list of clusters. Now we're still debating what to call these. We're calling them clusters of semantic clusters for COVID, semantic clusters for pulmonary. And the idea is that now that gives us a set of things that we can align. All right, so our goal is really to align. So this produces, you know, let's say roughly about 50,000 is what we, you know, produces more, but we selected about 50,000 of each. Right, and so we've got these little clusters. It found a central word with words around it, 50,000 of those from COVID, and then it found for pulmonary, again, 50,000 clusters, central word, and then the words around it, you know, and we have that information. So we create 50,000 each of these for COVID and for pulmonary. Then that's our data that we're going to align. So basically we have cluster COVID I, let's say, and we want to align it with some cluster pulmonary J. Why do we want to do this? Because these are made of 11 words, right? So they have around 11 words. So there's 11 words here. So there's 11 words here. There's 11 words here. Obviously, these are right now vector spaces, so they're just 128 vectors, but they're 11 words. So what we created actually is that it gave us those images, like the ones that I showed in the paper, right? So it gives us, for each one of the 50,000 clusters, we create an image, such as this one. And this, you know, this could be useful if you wanted to use like an image transformer. But the images are not aligned currently, right? So we just have the image, we have the images, but they're not aligned. However, vector graph doesn't just give us the image, it gives us something which is a lot more useful, which is it also gives us data structures. Okay, so it gives us an image, of course, per cluster, but also what we're calling the 11-word data structure, right? So 11-word data structure. And that's really something that we can actually use because, you know, that's 11 words. So it basically, it's not a sentence, but it is a cluster in this space. So it's a type of semantic meaning. So we're hoping that if, for instance, for pulmonary, it saw a lot of, well, you know, I wasn't feeling really well. I had these symptoms and I took this medicine. And so you keep saying that a lot in the corpus, and hopefully that concept, those words would be related. So that's sort of the intuition that we have there. And that would be similar for the COVID side. You know, the patient experienced these other symptoms and then they had these medicines and they did well or not so well. Okay, so that's basically the idea, okay, of having these right now. The problem that we have, once we have them, is that we don't have them aligned. So this data that we have is unfortunately not aligned, right? So we don't have Europarl, most of the data in the world, right? We're not going to be able to have something like Europarl, or we have the English and Spanish sentence, or something like that. So what we want to do is we want to create a totally unsupervised method that can digest tons of information and where we create some kind of a cluster. So we're in a sense taking the initial intuition of word to vec, right? So word to vec, there's the classic example of, woman is to man like queen is to X, right? So that, the X would be king, of course. And so we know that it has been shown quite extensively that word to vec does capture these ideas, okay? It captures these ideas. And so we're hoping that by doing this, there is some meaning between the clusters. Now, the next question is, how do we map them? Now that we have 50,000 data structures, right? 50,000 data structures. If you're curious of how we store them, we basically store them almost like an image. So we have for each one we have 11 words and 128 features, right? From the vector space. So pretty standard word to vec. So the 11 words plus we have one more, which is the ID, right? So the ID of the word. So that way we have the word, we have the vector, we can look it up, right? So that gives us this idea. So now that we have this, the next question that we need is, if these were aligned, if we had a corresponding COVID data structure of 11 mapped to a pulmonary data structure of 11, okay, then we'd be done. If we had 2 million of these, we can just feed them to the transformer. We'll feed the words, from the data structure, and we'd be done. But the last challenge that we have is, how do we do this? And this is the ongoing. So the data set, is ready. The transformer is ready. So we have anything between the data set, right? We have already the data sets. We have the transformer also ready to go. But in between, we still are working on the mapping. So this is something that we have, an approach that we are taking, and this would be, let's say, out of those two papers, the third paper in between, right? So we have a data set paper, a transformer paper, and then this one in between, which finally would do the mapping. So our approach is actually pretty straightforward on how we're going to do this. So the goal will be that, if you remember, going back to word to vec, we have a data set. We have a data set of COVID papers or abstracts. We have a data set of pulmonary, so COVID, pulmonary, and we created two vector spaces. So vector space for COVID, vector space for pulmonary. Now, to be able to kind of try to link them somehow, what we're going to do is we create a third vector space. And this, we call it both COVID and pulmonary combined. So this new vector space gives us the fact that we have all the words from pulmonary and all the words of COVID just in the one space through word to vec. So we use word to vec once again to create a space, right? We create that third space. And then we are going to use this. So let's say this is the third one. And then this vector space, pulmonary COVID, is what we're going to use to link them. Okay? So that's basically it. That's how we do it. So the idea is now, what do we have to do? Let's take an example. We have, we have the cluster from COVID. Let's say we have one, and it's of 11 by 128, and this one is 11 by 128. This is COVID. This is pulmonary. Those are just two clusters. So basically, it's equivalent to I have one of these images, which is COVID, and then I have another image, which is pulmonary, right? But I'm not using the actual image. I'm using the data structure of it. So what I need to do is, because these are words, right? These are words. I have the IDs, and I have the IDs here. Now all I have to do is I need to look up these words So let's add it here, the vector space of pulmonary and COVID. We just look up in there the vectors for those words, so for this cluster, we look for the 11 words in the vector space, we grab them and we average them. So we average them, then we grab the 11 words from this one in the vector space, grab the 11 vectors, average them. So now we end up with averages of COVID cluster and pulmonary cluster. And once we have that, hopefully by now you can see that, hopefully by now you can see, sorry. So just technical difficulty. Okay. All right, so I'm back here. So let me. There we go. So now all we have to do is we have the average in that space of the cluster from COVID, and we have the average from the cluster of pulmonary, but in this other space, the space that combines for both of them. So really what that gives us, if we imagine this is that vector space, the all combined vector space, now we have a cluster of COVID, right, averaged, and we have a one from pulmonary, a cluster, averaged in this space. So the advantage of this is that now we have all the clusters of pulmonary and all the clusters of COVID and so on. And now we have an easy way of finding the closest ones just in this additional space. So what we do is, quite simply, we take distance metrics, and we're just going to choose for every single cluster of the 50,000 of COVID, we're going to pick for each one the closest 10 or 20 pulmonaries. And the same for every pulmonary, we take the closest 20, and that will allow us to get, millions, right? So we can get 2 million, basically 2 million pairs. And now we're done, because now every cluster of COVID has been aligned to a cluster of 20, right? So from 1 to 20 of pulmonary. And then we do this. If we have 100,000 and then by 20, we get up there into the millions. And so this is how we basically solve the problem of getting the data. So at this point now, technically, we do have aligned data. Now, how perfect or great is it? That's another challenge, but we have basically our data set of maps, of map concepts, semantic concepts from the vector space. So very similar to, like I would have English and Spanish sentence. Now I have COVID cluster mapped to 20 of the closest pulmonary cluster and so on. We repeat this process. Now, we're going to try one last thing, which will be to use once we have these, basically once we have these 2 million, we can just feed them into the transformer. And then, the transformer that we trained for English and Spanish, we're going to feed it again with this data. Remember that here we have 11 words for each, roughly. So we're going to feed the words, right? They're not sentences, but they're just a list of words from closest to furthest away. We're going to feed that into the transformer, of course, and then we're going to measure. The results. Now, the blue score is usually applied to English translation in general. Here, this is a different concept, so we still we're going to have to do more of a qualitative analysis where we select, when we do the test, 1,000 samples that were predicted, and we kind of need to see the logic of it and then, go from there. So those are the results that we need to work on. Now, the last part, I only have 3 minutes to end the talk. So the last part of this is that we are going to use a Siamese network. So a Siamese network. And a Siamese network is basically a neural net where you feed 2 inputs, right? So for instance, we could feed inputs, and it compares them via, you know, CNNs, let's say, right? It compares the two images, creates vectors of them, embeddings basically, and then it compares them to see if they are similar, right? So this is a supervised learning algorithm. So we need to provide to this examples of a lot of things that were examples of similar and dissimilar. So we need to have similar and not similar. But we can also get that because when we calculate the distance metrics here, remember that, you know, we just performed for every C a matrix multiplication against all pulmonaries, for instance, and then it's going to give us the distance, right? So it's going to get, then we sort it. The top 20 will be the closest, and the bottom 20 will be the ones furthest away. So basically, we can use the top 20 as examples of similar, the bottom 20 as examples of dissimilar. Okay, so that is basically our entire approach. This is only so that given the data in the transformer, we can try to improve, you know, the qualities that, you know, we want to make more similar ones and more dissimilar ones. The images will also help us with this, actually, the images in the picture, because even though we're going to feed the data structures here, so the data structures of 11, we can actually, based on a paper called Deep Reinforcement Learning from Human Preferences. So in Deep Reinforcement Learning from Human Preferences from 2017 by OpenAI and DeepMind, they basically talk about how you can use techniques like providing a little bit of feedback to the neural net as the training is happening. So what we plan to do is every 2,000 iterations or so, we're going to print out 2 data structures, right? And there's just going to be a question for a human. A human will say, do you think these are similar or dissimilar? So the human will check one. That feedback will go back to into the network. Then maybe in the next 10,000 or whatever, we do it again. And so the idea with this is that, you know, it is not just learning on its own, but we're actually providing feedback. And that is just an idea we're borrowing from deep reinforcement learning from human preferences. And that's basically the work. So I think my time is almost up. So I'm just going to go back. So again, to summarize, so the data for this is here, right? So our we've created these NumPy arrays, which are, you know, 50,000 by 28 by 128 by 1, and these are basically the data structures of 11 that are so critical. For the feedback part, we're going to use the images. So we already kind of have them here, so we can just reference them by ID. And then as far as the transformer, we've already tested this with English to Spanish translation, and you know, we have in our Calix here in our website, we have the basically the examples of it, and we know it performs really well because it obtains a blue score of 39.79. So the transformer hopefully is the easy part of this, and really the hard part then just takes us back to the paper, right? The data set. Okay, so we have the images, we have the data structures, and now these were generated from the 2 vector spaces. We just need now to create the common vector space for each data structure, average the words, and then calculate distance metrics. And then a simple matrix multiplication would give us top 20 similar for every cluster and top 20 dissimilar. From that, we have aligned clusters of 11, and then we can feed those 11 words aligned with another set of 11 words to the transform. All right, so that's basically all my time for the talk. I hope this was of interest to you. I will post this on YouTube. If you have any questions about this project, you can just contact me through there. All right, so again, the title of our project is a transformer-based semantic engine for healthcare inference and search. And the research is being performed by my student, my grad student, Mitchell Burke, and myself. I'm Ricardo Calix. And that's it. All right. Thank you very much for your time.